to move on. So this is the adjoint system. Okay? So then the next point is that when you are dealing with controllability, you can simply make life a bit simpler and notation a bit simpler by saying if I am dealing with this system and the issue is whether I can go from any x1 into any x0 into any x1, in fact it suffices to consider x1 equals 0. So I can fix either the initial point or the target. I don't need to be, having them both free. I can fix just the target if you wish, or if you prefer, I could also take x0 to be, right? So, but then I prefer to do it that way. I go from x0 into 0. Why is that? Well, because the system is linear and time reversible. This is also something that is true for infinite dimensional dynamics, right? So the system is linear and time reversible, so you can always compute this trajectory that departs at time capital T from x1 and gets to some point y0. And then what I say is that the trajectory x, which matches x0 and x1, can be written as y plus z plus z, where y is the trajectory that starting at time capital T at x1 goes down to 0, and then z, which is x0 minus y0 at t equals 0, and 0 at the final time. Okay, so linear systems allow to add solutions to compute solutions. Now, of course, we are dealing with the same operator A, has nothing to do with the splitting arguments before. Finite dimensional dynamics are time reversible, and therefore it is sufficient to deal with the problem of going from x0 into 0. For instance, if you are dealing with nonlinear finite dimensional dynamics, time reversibility can be applied, but you cannot use this linearization, this addition principle. So in nonlinear dynamics, you have to really pay attention to initial position and target, right? Okay, so now I say that, in fact, control U is successful for the system, the original problem that was this one. The control U being successful for x, meaning that I go from x0 into 0, can be rewritten simply as this dual formulation. I claim that a control U is successful if and only if, whenever I take a solution of this adjoint problem and I do this computation here, this integral, I get this. Why is that? Well, I think the proof is written here. Why is that? Okay, take the equation satisfied by x. The equation satisfied by x, you remember, was x prime equal ax plus bu. You multiply by phi, scalarly at any t. So you get this equation for any t. On the other hand, if you go to the equation satisfied by phi, that was minus phi prime equal a star phi, where I am taking the adjoints, both in the time derivative and in the matrix A, and I multiply by x, I get also this identity, right? But now if I take the difference of this and that, I see the time derivative of the product x phi, right? Because what is the time derivative of the product x phi? Is x prime times phi plus x times phi prime. And when I take the difference of these with this, what happens? They go away, because if I transfer this a into phi, this gives me a phi, a star phi. So this goes away, and I get this. Now you integrate this from 0 to capital T. You write this. Now you transfer the matrix, from U into this, say, phi, the B, from U to phi with a B star, And then on the other hand, by integrating this from 0 to capital T, you have the terminal condition and the initial condition. Now, I wanted to get to 0, right? So this has to be 0. So then this is the condition written in a weak form. So this one here is like the weak formulation of the condition that the control has been successful driving the solution to the final time. Now, how many conditions there are here? Well, you could say that's strange, because on the arrival condition there were only n of them, right? X of t being 0, these are n conditions. And now I am replacing n arrival conditions, I am replacing them by all those conditions for every phi solution of this. But what is the dimension of the space of solutions of this adjoint problem? Is n. So this is an n component vector. So it is sufficient to take phi t to be any of the elements of the canonical basis, right? 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, and so on. Solve these n equations here as use them as test. So these are n equations as well. But these are n integral equations. So now you see that, and this is what is called the moment problem, right? This is what is called a moment problem. Exercise, read 5 lines about moment problems, right? So why this is called the moment problem? Because I am formulating the equation on U not as an algebraic or a differential equation, but I am writing it in terms of integrals of U against something, right? And how do you define the moments of a function f of x? You say, okay, the first is the integral of f, then I take the integral of f against x, then against x squared, and so on. So here, this is a moment problem in which you are integrating U against who? You are integrating U against the n objects you get by doing b star phi out of the n canonical solutions of this adjoint problem. Okay? So now the question is, once I get to this point, I say, is there an easy way of solving this moment problem? So you see, the simplest manner of solving a moment problem, here you have n equations, is if for any reason this was the n partial derivatives of the same function, right? If these moment equations here were all related to the partial derivatives of the same function, it will be very easy to solve, because it will be sufficient to find a critical point, a minimum of that function. Can you see here the partial derivatives of some functional of the calculus of variation? Do you see here some kind of variational structure on that problem? You remember, right? The calculus of variation approach for solving systems. You say, I want to solve this system, AX equal B. But actually what I do is I write this as AX phi equal B phi for every phi in Rn, right? And now I realize that this is just minimizing the following functional, provided A is symmetric. So if you minimize this functional, or you in general compute any critical point of this functional, you are solving this. Saying that the n partial derivatives of that functional at a given point are 0 is equal to saying this, and is the same as solving this equation. Now that you have seen that example, could you guess what functional I have to minimize in order to get these n equations here? Let me do this. See what happens. Maybe it's written here. Let me do this.
How can you make sure that this minimum isn't minus infinity?
Well, provided A is coercive. You have to assume that A is coercive, right?
Okay.
Yeah, of course. Yeah, I mean, in general, any critical, what is correct is that if A is symmetric, any critical point of this functional is a solution of this and a solution of that. Now, if you want to make sure that this is minimized, then you have to assume that A has coercivity, right? Otherwise, it could be some saddle point or a max. You are right. But the key is, how do you rewrite a system of equations into the weak form, and then you are able to guess what is the hidden functional for which you are computing the critical points, right? And then here, you do the same. You start from a hard problem, which is formulated in terms of trying to bring x to x1, or to 0, in particular in this case, without loss of generality. I start from this hard problem. I write it in a weak form, in this way, right? And I end up realizing that the functional that I have to minimize is this, right? Now, what is this functional about? You see, in this functional you identify, like in here, there is a quadratic part and a linear part as a function of x, right? Quadratic plus linear. So here what I do is the following. I have a functional defined in Rn. How is this functional defined in Rn? For any phi t, I first solve this adjoint problem. This is solving ODEs. Out of this ODE 7, I get the phi. And once I get the phi, I build this integral from 0 to t of b star phi squared. Plus x0, the point to be controlled, the initial point, times phi 0, which is the value of the adjoint state, solution of this, at time t equals 0. Right? And my claim is, if you are able to find a critical point of this, then the corresponding control is simply b star u hat, phi hat. This is nothing to do with the Fourier transform. This is just a notation. The notation corresponding to the minimum or the critical point of this. Why? Because if you compute the Gateau derivative of this, or the partial derivatives of this with respect to j, what you get is that this guy, b star phi hat, fulfills precisely the conditions here. So now, the point is that we have reduced the problem of controlling the system into a problem which is much nicer. It's just minimizing functions. There is no control anymore. Right? So not only this is a different characterization of controllability, but this is also giving you a methodology to compute the control, right? How would you do it? It's very simple. You need to compute the control. Well, I take this functional and I minimize it in the computer. Okay? How do I minimize it? Well, I discretize the functional, I discretize the ODE, I discretize everything, and I minimize, right? And this will be more or less the optimal control. Then, in fact, you can actually use this methodology even without checking the Kalman rank condition, right? You can minimize anyhow this functional, and this will be like least squares. You will get the best you can. Some cases you will get to 0. In some other cases you will realize this is like the car in the space. I mean, some dimensions, some components will not be controllable. Okay? Now, you see, quadratic plus linear. This is a continuous functional in Rn. Rn, which is the Euclidean space. This is a nice finite dimensional Hilbert space. This is a convex function. In order for this to have a minimum, the only extra condition you need is what? Coercivity, right? You have to avoid the possibility that this is not positive enough, right? And therefore, in order to do this, you need the coercivity, you need this kind of condition, right? This coercivity. And this is the observability inequality. This is the dual problem by, now I rush, because otherwise we will never get away from the introduction in this course, okay? And then my job was to do the wave equation, so I have to. So I rush. So this is the observability inequality. I could have done that in the first lecture, but maybe then this will have been too fast and not very useful, right? So this is the observability inequality. This is the dual problem that Wiener was saying. Control is equivalent to communication. Now, the game to play is, people prefer this problem, normally. Why? Because there is no control here. You see, now dealing with the control is complicated because you have to always think in terms of control and solution. You have to build the control to compute the solution, or by the contrary, in some cases, you can build the trajectory and then read off the control, but this is quite unnatural and hard to do, except in very simple cases. This approach is much nicer, because now there is no control anymore. I am dealing with this nice ODE system, no control. This is just a free ODE system. Except for the fact that, you know, I'm calling A star to A, but this is a notation, and I am changing the sense of time. That's something I can, you know, if you want, I can avoid by simply changing T into capital T minus T. So this is simply a linear ODE system. And the question I am asking you, right, and this is why this is called observability, is could you please tell me whether out of this measurement here, I can recover full information? This is something that is very important also in all kind of inverse problems, right? Like in imaging, right? When you go through some computer tomography, or you know, like you know, or you are looking for some natural resources like oil, right? So you get only partial information, some, you know, images given by satellites, right? And out of it, you have to recover the full energy of the solution. So consider, for instance, the case where there was only one control. M was 1. So phi has n components. N is huge. You know, 10,000 components on the state phi. But then M is 1. So what is B star phi? B star phi is just one linear combination of all the components of phi. So you see that out of all the components of the system, you are seeing only one linear combination. But of course this will be in general insufficient. But you are doing it a long time, right? So you are observing during the time interval 0 capital T, and you are integrating, right? So this is like you are observing, you know, the room next to through a little hole. Of course, you cannot see the whole room, but if people were walking on a circle, right, after some time, you will be able to say how many people there are, right? So this is the same. You are only looking through this B star, right? But the system, right, the system here, the system is evolving, is rotating, right? So because the system is rotating, the question is whether or not the rotation is sufficient so to make sure that through B star you see everything, right? And this is the inequality you have to prove. Okay, now we are in Rn. In Rn, all norms are equivalent. So in order for this inequality to be true, the only thing you need to guarantee is that this quantity here is really a norm. Right? The only thing you need to guarantee is that this quantity here is a norm. Because in Rn, in the Euclidean space, all norms are equivalent. Okay? And then in order to guarantee that this guy here is a norm, the only thing you need is this uniqueness property. So this uniqueness property says, in case you look through the window, the narrow window B star, and you see 0 all the time, then I know there is nothing inside. As soon as I have this uniqueness property, I repeat, this guy here is a norm, and because I am in the Euclidean space, these two norms are equivalent. This functional then over here is coercive. It has a minimizer, and the control is simply B star phi tilde, where phi tilde is the minimizer of this functional. So not only I have a new characterization of controllability, but I have also a computational method in order to actually build controls and control trajectories. Okay? Now, well, I mean, this condition has to be equivalent to Kalman, right? Why is that? Why this is equivalent to Kalman? Let's write phi. What is phi? Phi is the solution of system phi t, right? So this means that phi t is exponential a star t minus t applied to phi t, right? Do you agree? At time capital T, I get phi t, and on the other hand, if I compute the time derivative, I get this. And my claim is that this here is an analytic function. Okay. So this here is an analytic function. You know what analytic functions is? Probably not, but I am not telling you this. I mean, have a look if you wish, right, in the Wikipedia. So, but analytic functions are precisely those that can be developed in power series. And this we know, because we have the power series expansion of this the same way I wrote yesterday, right? And if there is something that changes completely with respect to classical smooth functions, is that, you know, analytic functions can never take off, right? So if someone sells you a ticket for a low-cost flight, you know, claiming that the trajectory of the airplane is analytic, don't buy it. Airplanes cannot take off in an analytic manner. They can take off in a Lipschitz manner, right? That will be a bit unpleasant, right? It will be something like this, right? They can take off, you know, like in a C2 manner. They can be very careful about how they take off. Maybe they can even take off in a say infinity manner. I mean, if the pilot is very good, he can guarantee say infinity because all the derivatives vanish, but they can never take off analytically, right? Why? Because analytic functions have the property of unique continuation. It means that if you are 0 to the left, you have to be 0 to the right, okay? And this is simply because there is a power series expansion. If you are 0 to the left, then the first derivative, the second, the third, all derivatives are equal to 0, but then the power series expansion is equal to 0, and you have a neighborhood of convergence. So because of this power series expansion, you can never be 0 to one side. You have to be 0 also to the other side. This is what is called the property of unique continuation. Why is it called property of unique continuation? Well, because unique continuation means that something that is 0 to the left is also 0 to the right. If you want to take off, then there has to be a second possible continuation. So you fail to have the property of unique continuation. Okay? Of course, it's unique and it's the simplest one. In this case, 0.
What person developed this?
Who? What? Of these analytic functions or unique continuation?
Of observability.
Yeah, this can be, you know, well, this is a personal view to this, but you can very much see these kind of ideas. There is a very nice article by Jacques-Louis Lyons written in Siam Review back in 1988, right? And, you know, these ideas are somehow there, right? Okay, so now I say, oh, then you are telling me that I have to check this unique continuation, but this function is analytic. So for a function that is analytic, being 0 all the time is the same as having 0 derivatives at a given point. So B star phi t is equal to 0 for all t if and only if all the derivatives at any order of B star phi at t equal to capital T are equal to 0. Okay, I give you 1 minute. Write this in a piece of paper. What do you get when you write this? Write the fact that B star phi, taking into account that phi has this exponential representation, at time t equal, capital T is equal to 0. Give you 1 minute for this. Okay, did you get that?
Yeah, minus 1 to the power n b star k minus 1. I mean, if phi t is.
So what do you get here? B star. So what do you get here? Minus 1 to
n, a b star, a star, n to n minus 1. No, n minus 1.
n minus 1. Okay, good, great. Thank you. So what you get is something similar to what the Kalman rank condition was, right? Not the same, but it's somehow related, right? So what we get is that, you know, this was the Kalman rank condition. Now what I get is this, right? What you are telling me is that B star, A star to any power of phi t is equal to 0, right? So the only way in which B star phi can be 0 is that phi t is so that B star A star k is equal to 0 for all k, right? This is what you are telling me, right? San? No?
Yeah.
So we say, repeat, assume B star phi is equal to 0 for all t. This being analytic, this means that all derivatives at t equal capital T are 0. But as you have computed, right, this is simply this. Now, Cayley-Hamilton theorem. If this is true up to n minus 1, after that, this is done, right? So I only need to check this up to the power n minus 1. So now the question are asking me is whether the kernel of this matrix here is reduced to 0. If the kernel of this matrix is reduced to 0, the only vector phi t fulfilling all these conditions is which? Is the 0, 1, right? And this is precisely the unique continuation condition I needed. And now, what is the kernel of this matrix? Is the perpendicular to the image of that one. So whenever the image of this matrix here is full, the kernel is reduced to 0. And then you see the duality. Okay? So now, what is the beauty of this theory? The beauty of this theory is, I know some of you work with infinite dimensional systems. Like, you know, they are interested on dynamical systems in infinite dimensional spaces. I mean, if you are doing partial differential equations, models in elasticity, in fluid mechanics, they are most often PDEs. Well, we have done also the PDE theory in one shot. It's the same. It's the same theory. Now, the only thing that changes in finite dimensions is that you don't rewrite this in terms of the Kalman rank condition, because n is infinity, and then you will have to take infinitely many, you know, powers and so on. So, but the fact that whenever you have observability, the system is controllable has been proved in full generality, and the proof is the same, right? So now I repeat. Let's go back. Now, assume your system was not written in Rn, but this was written in some Hilbert or Banach space, right? But A is the generator of a semigroup, and B, the control operator, is so that this system is well posed. And then you ask me, is the system controllable to 0, right? Okay, then I tell you the system is controllable to 0 if and only if the adjoint system here, right? The adjoint system here is observable in the sense that the inequality here is fulfilled, right? The same proof. Furthermore, the bonus is that not only you know that the system is controllable, I have given you a computational method to actually get an approximation of the control. What is the computational method? You build this functional and you minimize it. How do you minimize it? You apply a steepest gradient descent or some kind of variant to it. So everything in one shot. Now, remark, warning, danger, forbidden. If the system is infinite dimensional, don't try to write the Kalman rank condition where it was. It was somewhere here, right? If the system is infinite dimensional, don't try to write this Kalman rank condition. Why? Because n is infinity. And even if you write it for infinity here, because you go to any order, I mean, you are, you know, you apply some recurrence formula, you go to any order, and you can check that the rank is higher than any integer number. This will make sense. Even in that case, you cannot guarantee that the system is controllable, because it could well happen that, for instance, the system has infinitely many components, 1, 2, 3, 4, 5, and you are only controlling the even ones. I mean, if in an infinite dimensional system you control an infinite number of components, you already have this with infinite here. But this is not sufficient because you are still missing all the others. You see the point? So the only change from finite dimensional controllability theory into the infinite dimensional controllability theory is that please don't try to rewrite things in algebraic terms. All the rest is the same. So now the game to play is whether if you are dealing with PDE. So who is working with a PDE in his thesis? So any of you is working with PDEs? Yes. So what kind of PDEs are you working? You, for instance, Charlotte, you were working with? Sorry? Nonlinear beams. So this is a linear theory. How do you go from nonlinear to linear? Is by linearization, right? Okay, nonlinear to linear, you linearize and you apply the same theory. So with an extra effort, you get nonlinear, at least local deformations for nonlinear beam equations. Now, what is the game to play? The game to play is that you have to take your nonlinear beam equation, linearize it, and prove this kind of inequality. And this, of course, is delicate and has to be done carefully in each case. Okay? That's all.
So in infinite dimensional system, we always check for the dual problem.
Right. You better go to the dual because the direct problem is very hard to understand. There are infinitely many equations, right? These moment problems, sometimes there are ad hoc methods to solve these moment problems here, like the one written here. Like for real exponentials, this was done by Fattorini and Russell in the 70s for one-dimensional heat equations using, you know, quite refined theory of real exponentials and so on. But this is very specific to some of the problems. More generally, it's easier to deal with this specific problem of proving observability. But now, of course, this is just a matter of taste. If someone tells you, no, you know, I have a book here on moment problems, and I check chapter 13, I have the solution to the moment problem I need, it's fine. If you have a solution to the moment problem, you also have an inequality. Sometimes it could be easier to find, you know, the solution to the moment problem than, you know, proving this coercivity, right? This is like, you know, this is a matter of taste also, right? I tell you, okay, I tell you, for instance, I know that this system has a unique solution provided A is coercive and symmetric. Yeah, and you tell me, yes, Enrique, that's, I mean, that's very nice, but you know, I don't have time. I will not check whether this matrix is coercive or not. I just apply Gaussian elimination and I get the solution, right? So this, the matrix being coercive, right, is about this kind of inequality, right? While some cases, you are lucky enough to observe that the problem you needed to solve in terms written in moment problems, for some reason, you know what the solution is. Now, what is the bonus of proving this observability inequality? Is that you have a tool to compute controls, which is quite robust, right? So because assume today you have to compute the control for x0, and tomorrow you tell me, no, tomorrow is not x0 anymore, it's an x0 plus some error epsilon. What do you do? Well, you run the same minimization code again, and you will get the control for the new problem, right? Or, on the other hand, you say, well, you see, Enrique, B has changed a little bit today. Well, you use the same idea as before. If there is observability, there will be observability for the neighboring Bs. You apply the same tool again and again. Okay, so this is much more systematic, and in particular is much more adapted to computational purposes. Okay, and this can be extended to PDE automatically, right? Good. So let me just give you, because some of you were asking me about nonlinear systems. Now the system is nonlinear. It's true that I was too much talking about linear systems. Assume now the system is nonlinear, right? Right, where n from Rn into Rn is, say, C infinity is smooth, or C1 is smooth, but non-linear. Right? As Charlotte says, she is dealing with non-linear beam equations. Or if you write the equations for Nelson Carr, I don't know whether you checked yesterday in the Sontan book, then they are non-linear because there are sinusoidal functions everywhere, because of the angles and so on. If you write the dynamics of the Nelson Carr, it's non-linear. So the dynamics is non-linear immediately. And then you say, Enrique, you spent like 10 hours, you were talking only about linear problems, this is useless. So, no, I tell you, no, with a little effort, you get also some bonus for nonlinear problems, right? What is the logic you have to apply? Okay, when you are in nonlinear problems, as I told you, you cannot say anymore, going from x0 into x1 is the same as going from x0 into 0. You have to say also the target. This is like going to the Everest. Did any of you went to the Everest?
Bit down.
Bit down. How high you were?
I was close to around 5,000.
5,000, good. I mean, that's. Anyone went to the Mont Blanc? Did anyone go to Mont Blanc? No. Okay. Anyhow, we all know that it's not the same going from 1,000 to 1,500, or going from 4,000 to 4,500. And it's not the same going from 7,500 to 8,000. Otherwise, everyone would go to Everest, right? So the problem is nonlinear, right? This is a very clear case of nonlinearity. So here is the same. When the problem is nonlinear, the idea is that you can somehow linearize the system and control, but you have to do it by pieces, right? This is why if you go to the Everest, you don't go one day in the morning and again get in the evening, right? You do it stepwise. Okay, you camp, then you rest, you recover forces, and you go back again. Okay? So you have to do it stepwise. So the same for nonlinear systems, right? If you are controlling a nonlinear system from one initial configuration to another one, the first thing you need to do is to build a bridge, right? So you are working in this space, you have to go from x0 into x1. The first thing you do is you look for a bridge, a path. And once you have built the path, you walk along this path on small arcs, right? So the question is whether you can drive the system from here to here. You have still to implement the control, because you know, if you look to going to the Everest, is possible? Yes, it's very simple. There is a path here. Well, still you have to walk it through, right? So there is a path, yes, but do you have enough energy to steer the system from one to another, and are you smart enough to drive it from that point to the other without exiting the road, right? Okay, this is like you know, these games, right, where you have to drive a car on the computer very fast. I mean, the idea is very simple. It's just, you know, keep the car in the middle. It's not because it's simple that it's easy to do, right? Conceptually simple, but hard to implement. So here is the same. You have a path, yes, but this is a path in the space. Now I have to make sure that I can, right, choose u at any time so that the solution of this system is, you know, remains close. So this means that roughly controllability of nonlinear systems is a delicate matter, and you have to do local plus glue to get something non-local. Okay? So nonlinear analysis very rarely can be global. Whenever you are approximating solving control or equations which are nonlinear, you have to do that locally and then glue patches to have a global solution. Okay, so let me now show you how do you build one of these patches, right? So the best you can is not the only thing you can do, but one of the most fundamental ideas is look for some steady state. What is a steady state? A steady state is just a configuration where nx bar is equal to 0, right? nx bar equal to 0 is a steady state solution of the system, right? Why? Because if you find an x bar so that nx is equal to 0, then x bar time derivative, which is 0 because x bar is time independent, plus nx is equal to 0. So this is a particular solution of the nonlinear dynamics, which is time independent, and we call it a steady state, right? A very good candidate for this being the case is always the 0, 1, right? Right? If you give me the wave equation by D'Alembert, something like this, do you know any steady state solution? Yes. 0 is a steady state solution, right? And if the problem were nonlinear, 0 will be a steady state solution also, right? But of course there could be on any other steady state solutions. Okay, now you have a steady state solution. You say, I would like what? I'm working near this steady state solution, so my goal will be now whether I can find a small disk, right? Whether whenever x minus x bar is less than epsilon, and the target x1 minus x bar is less than epsilon, whether there exists a mu such that x of t is equal to x1. Okay? So this is the question. Can I find a neighborhood of this steady state so that any point which is close to the steady state can be driven to any point which is close to this steady state? In particular, can I drive any point in this neighborhood to the steady state itself? Actually, if I can drive any point to the steady state, then probably I can drive any point to any other point, right? Because this is the steady state x bar. Taking a point, if I can go there, and then I have here a target, if I go here that way, then I can link the two trajectories and go from one to the other, right? So what is then the principle? The principle is that if you simply use the inverse function theorem, because the linear system is controllable, then you also have the local controllability of the nonlinear one. But what is the corresponding linear system? It's the linear system in which you replace this by the linearization. And what does linearization mean in here? It means that, you know, in general, how do you linearize a nonlinear system? And this is what automatic differentiation does for you on the computational code. But before you use automatic differentiation, it's good to know what you are doing. You are so-called computing the sensitivity of the solution with respect to parameters. Did you ever heard of this sensitivity analysis? Sensitivity analysis is what? Is you modify the parameters a little bit and you see how the solution changes, right? So here, this is what we are doing. I say, this is the solution. Now I modify the initial datum a little bit. I add to x0, I add epsilon y0, right? I modify the initial datum a little bit by an epsilon in the direction of y0. I would like to know how does x change. Then x will be the solution, say, R, the reference solution, plus epsilon y, where xr is what? Is the solution of the state equation with initial datum x0, right? And y is what? What's going to be y? What is going to be y?
The solution with initial condition epsilon y0
is the solution with initial condition y0. That's correct, because there is, in some sense, there is coherence, right? If x is taking the initial datum x0, y is taking the initial datum y0, and I add them with an epsilon multiple factor, then the initial datum is correct. And what is the ODE that y solves? For x reference, I solve the nonlinear problem out of the reference configuration x0, which is the one that I am, taking variations of. But now the game, and this is the delicate matter, is what is the ODE that y solves? I take the same nonlinear ODE. Well, there is no reason for this to be the nonlinear ODE, because f of x plus f of y, when f is nonlinear, is not related to f of x plus y. So what do? I'm actually doing a Taylor expansion, right? A power series expansion. So what's going to be y? Okay, let's check. Candidate for y. What do you put on the right hand side? For x, I have f of x. So for y, what do you suggest?
The first derivative of
the first derivative of f, good. Evaluated where? In the reference solution xr, and multiply by y. Thank you. So this is a linear dynamics, right? A linear dynamics. Oh.
Don't we need an epsilon term?
Yeah, here.
Because in the differential equation.
No, here there is not epsilon term. The epsilon goes there, right? Of course, you can also justify all this by using power series expansion, and there are cases where in control systems you can even go to higher order terms, right? If you don't see enough in the linearization, you can go to higher order terms. But now you see that immediately you have proved the following. Assume, as we said before, there was a steady state. And assume you have proved that this system fulfills the rank condition. So what is this system? So here I take the derivative of the nonlinearity at the steady state, which is a matrix. In case this pair fulfills the rank condition, the nonlinear system will be locally controllable. Just use this linearization argument plus the inverse function theorem. Okay? So this is for those that are interested on nonlinear. So, well, we were very late, but now we are finishing the course because I did infinite dimensional systems and I did nonlinear. So what else? But this is important. You keep the ideas are always the same, right? So you might be doing nonlinear beams. You can be doing nonlinear Navier-Stokes. Doesn't really matter. The ideas will always be the same. Nonlinear, you have to go by pieces in a piecewise manner, locally, work locally. Then you linearize. When you linearize, you have a linear system. Then, you go to the adjoint and you look to this observability inequality. Oh, by the way, I wrote this for autonomous systems. But the same applies for non-autonomous systems, right? So another bonus you get is that if you were dealing with the time-dependent systems, linear finite dimensional time-dependent systems, so far everything I have said was for the particular case where A was independent of T. And I could use this very simple representation, exponential AT. Now, if A depends on T, there is not such a nice simple representation. Again, the Kalman rank condition is not that easy to write. But this philosophy is completely true. So the controllability of this system, is completely equivalent to the observability of the adjoint. And the observability of the adjoint is written exactly in the same way. It makes sense. You simply, rather than taking here the solutions phi of the previous system, you will take the solutions phi of the non-autonomous version of that system where you are taking the adjoint of A at any t. And from a computational point of view, it works as well. Because once more, the control is computed by simply minimizing this quadratic functional. How do I do it? Apply a steepest descent plus some kind of discretization of the ODE or PDE you are considering.
But the adjoint of A is still time dependent, isn't it?
Right. But so what? You discretize the ODE, which is time dependent, you can apply the same numerical schemes, right? So the the Euler implicit numerical scheme converges also for time dependent numerical schemes, for ODEs. Yeah, so what I'm trying to say is that if you adopt this point of view, the theory becomes completely general. It's not limited to finite dimensions. It's not limited to adjoint systems, to autonomous systems. Can be applied in infinite dimensions, can be applied for time-dependent systems. And because of that, you can linearize nonlinear systems around points which are not steady states. Because in order to get constant in time coefficients, you need to linearize around, a steady state. But if you linearize a system around a periodic orbit, when you linearize, you will get, of course, coefficients which are time-dependent and periodic, right? So you need to apply this version of the theory. One more extra bonus of this theory. The control you get that way is unique. Not only you are computing one control, actually you are getting a very robust, unique control. Why? Because whenever this coercivity inequality is true, there is a unique minimizer for this functional. Does this mean that this control is the unique control for the system? No, there are very many. This is what we have drawn before. You remember? I told you before, in that very particular case where I said I had to go from one initial configuration to the other, and I said it's very simple, you just be very careful, right, on matching here the initial and the terminal conditions, and then you do whatever you wish. And then I said, well, once you have one way, you can do many others, right? So generally speaking, when a system is controllable, there are many ways of controlling the system. Okay? But the good news about this method is that this method gives you, in a systematic manner, a robust, say, toolbox to compute only one of them. Always one of them. Always the same. You modify the parameters a little bit, the control changes a little bit, but you are not jumping in a capricious manner from one type of control to another type of control. The control depends smoothly on the parameters of the system. For instance, if you are dealing with a viscous fluid problem, if you change the viscosity a little bit because you are regulating better the lab experiments to better fit the value of the viscosity, the control will depend on the viscosity in a smooth manner.
Can we say that this is the most optimal control?
Yeah, precisely. We are going back to this, okay? So in which sense this is optimal, but yeah, it's optimal. And in particular, this means that this control will depend smoothly on the parameters.
Do you sense, in some sense, it is optimal? I mean, what sense?
But this is later. You have to wait 2 more minutes to get to this. So this control also depends continuously on the time horizon. Assume you were controlling time 0t, you know, and Yichen is doing it for t plus delta. You don't get the same. But if you apply this toolbox, the u and the u delta you get are very close, as it could be expected. Right? But you see, other people could have a different idea and say, listen, I know how to build controls which are totally different. So you wanted to go from x0 into x1. You wanted to go from x0 into x1. I am applying this, and you see, one of the properties you see in this control is that typically this control will be active all the time. It will never rest. Right? So this is like PhD students. You are active all the time, right? You never rest. You always work in the PhD thesis, right? So this is like an ESR control. We could call it ESR control. Never rest. Why? Because, you know, if this control were 0 for some time interval, it will be 0 every time. Why? Because we have the unique continuation property. So because of the unique continuation property, it means also that this control never rests. So there are other control trajectories that you can implement, but this one will never be implemented by, you know, like that. So let me show you, for instance, the lazy control strategy. I mean, which of course ESRs don't do, right? Lazy control strategy is you say, you do nothing, you do nothing, you do nothing. The system goes down, the system goes down, the system goes down. The system. Oh, and then the day before you say, oh, I have to control the system for tomorrow, and then I add a lot of control to bring the system here. So a control that is 0 for some time and then controls the system, is there such a control or not? Can we guarantee that such a control exists? Yes, because the system is controllable in any time. So you give me time 0 capital T, but then I decide that from 0 to capital T minus epsilon I do nothing, and all my effort will be concentrated on the interval T minus epsilon capital T. Of course then the cost will be huge, right, because I have to control the system on a time interval, right? But you know, I could also control a little bit and then, oh, I'm tired, let me go to bed, right? And then the system will go down, and then I control again. So this kind of control that in which you take an arc, 0, and then a second arc, this is also possible. You can apply many strategies, right? There are infinitely many ways of controlling the system. But this one only gives you one. Always the same one. And it will never rest, right? So actually, and this is an exercise, so show that, I mean, this is not an easy one, but try to do this exercise. Show that the control U obtained this way is of minimal L2 norm among admissible controls. Okay, so this clarifies your question, right? Shan, you were asking, I mean, you are saying that the control is optimal. I have said it has many properties, has been generalizable to time-dependent problems, to infinite dimensions. depending continuously on all parameters, the initial data to be controlled, the time window, the coefficients of B, the coefficients of A. But in fact, there is one further property. For a given system, in a given time t, and given an initial datum and a target, this is the control of minimal norm, the cheapest one in some sense. Okay, so this is a different way of measuring optimality. Good? Right, precisely. So this is related to Pontryagin principle, right? Actually, if you write this is a very good question actually. Let me write it down. Let us write down in a unified manner what we have done. We have taken the system like this with initial datum x0. I have got x of t to be x1, the target. I have found that u is b star phi, and that phi fulfills this system, right? We have done all this. Because the system was controllable, we have built a solution of the adjoint system so that b star phi, this solution that now I don't denote by phi tilde, I know is going to be the minimizer, but this solution of this adjoint system fulfills that, right? Okay? If you wish, you can write here u being b star phi. Okay, and what do you see then? This is the backward forward state, adjoint state system coupled together, right? Well, you could say, you see, I'm not afraid because I know that all these systems can be equally solved in any space dimension, right? I could say this plus this, eventually I can change the sign here into a minus. I see this and this as being an ODE system of dimension 2n, right? N components for x, n components for phi. Good. But then you will tell me, in order to solve this system, I will need initial conditions on x and on phi. I need 2n conditions. Do you have here initial conditions for phi? No. Actually, you have n conditions for x at 0 and n conditions for x at phi, at capital T. So this is not a classical Cauchy problem, right? So this is a joint system, a joint state equation, but you have initial and terminal conditions that are not standard and you cannot solve using the classical, say, Cauchy theory. Actually, if you have to solve this system, how you will proceed? You have to solve this system, how you will proceed. In fact, You know, you have a solver, you have your ODE solver, but the ODE solver says, no, no, you have to give me the initial condition. You have to give me the initial condition. You will try to somehow relate the initial condition of phi with this terminal condition, right? If I had a dictionary to say, you know, what is the phi 0 that corresponds to the target x1, that will be great. But this dictionary is precisely the control toolbox, right? And there's nothing easy, right? So you don't have that dictionary, you know you don't. But you have the solver for the ODE. What you will do, you will build an iteration algorithm. What will be the iteration algorithm? It will be take some phi 0, right, and solve system 1 plus 2, 1 being this equation and 2 being this one, with initial datum x0 equal x0 and phi 0 equal phi 0. You solve this system in a unique manner. Then there is no problem. This is a system, linear system of ODEs. N ODEs here, N ODEs here. You solve forward with your solver. Out of these two equations, one is guaranteed, is the initial condition, right, which is here. Right? And then you compute this. If this is 0, you are done. But this is very unlikely, right? And if this is not 0, you have to correct phi 0 a little bit and try again. This is what is called the shooting method, right? Right? This is the shooting method. You have to, this is what you do when you have two boundary value problem for ODEs. What do? You shoot. Oh, sometimes you go too far. Then you say, okay, let me shoot with a less angle. Then, oh, now I am too short. And now I use a bisection, you know, algorithm until eventually I get to the point as precisely as I wish. You see, if you write this, you know what is going to be? This is going to be exactly a steepest descent algorithm for the minimization of this. Okay? So your question was, is this related to Pontryagin maximum principle? Definitely. This is the Pontryagin maximum principle applied to the controllability of a linear system. And actually, the methodology you are building through the observability inequality and the minimization of this functional is equivalent to writing the Pontryagin maximum principle, realize that this system is non-standard because you don't have you don't have initial conditions, but you have half of the initial condition and half of the terminal condition. And then you implement an iterative shooting algorithm. Okay? Good. Okay, bang bang. Assume you want bang bang controls. You see, these controls here are very smooth. You know, the controls we have got are analytic in time. They are very smooth because you are taking the solution phi of the adjoint system, which is say infinity smooth, and then you are looking just the projection B star. So being smooth is nice for a mathematician, but it's not necessarily nice when you are trying to compute, right? Because you have to follow, you know, a very complicated arc, right? So in practical applications, people say, no, no, I prefer bang bang. Because, you know, bang bang is on and off. So I have a switch, And the only thing I have to do is to decide when I switch on and when I switch off, right? So now my point is that once you have understood this, you can design many other controllers, in particular bang controls. So in order to design bang controls, it is sufficient to minimize this functional and not the one before. You see the difference between this functional and the one we had before? What is the difference? The square is outside. Actually, why the previous functional was a good one? You had j phi 0 that was 1/2 of the integral of 0 to t of b star phi squared dt plus x0 phi 0. And we said I minimize j. Minimize j means, well, this was for phi at time capital T. Sorry, I was doing it that way. This was the functional I was minimizing before, right? Before I get here. And I was minimizing j. And I said, this is a good control. Why? Because if the minimum is achieved, it means that the gradient of j at phi t is equal to 0. And this means actually that the gradient in any direction is equal to 0. And this is exactly the same as saying that the derivative with respect to epsilon, right, computing any first variation of j is equal to 0. Right? Okay? And this is equivalent to saying that the integral from 0 to t of the derivative of this, which is b star phi times b star psi plus x0 psi 0 is equal to 0, right? And this is exactly like saying that this is the control I was looking for. This was the proof, right? So the Euler-Lagrange equation, the first order variation of the functional I was considering, was giving me the control because precisely of that reason. If I minimize this functional, I get in the weak form the first derivative of, you know, this equals 0. Now, I modify this functional and I say, I put the square outside. I ask you, do you know whether this functional will have a minimizer? Again, this is continuous and convex. What do I need? Coercivity. What is the coercivity? Coercivity will be now proving whether this inequality is true. Coercivity in this context, right, of bang will be about proving this inequality. So this inequality is not exactly the same as the one before, right? In the one before I was taking the integral of the square. Now I'm taking the square of the integral. Which one is better or higher? Which one is more stronger? The first one, right? Because the L1 norm is bounded by the L2 norm through Cauchy-Schwarz. So this one I have to prove it, right? How do I prove it? I do the same. I say, in case I am in finite dimensions, I use the same argument. All norms are equivalent. So I have to check that this is a norm. But checking that this is a norm implies that whenever this is 0, phi is 0. But this is the same we have proved before. This is the unique continuation. So this inequality is true, and then I have a minimizer. But now, when you compute the derivative of this, what do you get? When you compute the derivative of this square of the integral, what do you get? You get 2 times the integral, which is a number, times the derivative of what is inside. And what is inside is what? The derivative of the absolute value is the sine function, right? -1 to the left, plus to the right. So what you get is this kind of controls, right? So when minimizing this functional, what you get is a control of this form. The integral from 0 to capital T of B star phi at the minimizer, which is a number, this is a number, times the sine of B star phi. And what is this control doing? Well, this control is switching whenever this guy changes sign from plus to negative. This is switching from +1 to -1. And of course there is an amplification factor, capital M, that you have to know what it is. And again, it will depend on how long the time interval is. When the time interval is very long, right, then the amplitude of the control will be smaller, so you expect this M to be smaller, right? But when the time capital T is very short, you expect the control to be very large in size, right? And then you expect this to be, higher in amplitude. But it's always bang-bang form, in the sense that it's a switching from, say, -M to M and M to -M, right? So this control here, which is bang-bang, is also optimal. But you know in which sense it's optimal?
Because it's following the gradient.
Yeah, but in which sense? The one before was optimal in the L2 sense. Now this one is going to be optimal in which sense? This is going to be optimal in the L infinity sense. So this one, exercise, proved that the BB control is the one of minimal norm in L infinity 0T Rm. So what is the idea of this optimality? Let me explain you why L infinity optimal controls are bang-bang. Let me explain you why L infinity optimal controls are bang-bang. So assume the control you are looking for, or you find, is you find some defect, right? So this is M minus M, right? And this is the control you found, right? M minus M, M minus M, M, then a continuous arc minus M. You tell me, I found this control. From 0, this is time, from 0 to capital T. You tell me I found this control. I tell you, this is not optimal in the L infinity sense. Why? Well, because it's not bang-bang. What I'm claiming is that bang-bang controls are those in which the L infinity norm is minimized, right? So you have compressed the control, from the top and from, down in the maximal way. So I see this drawing and I tell you, no, this is not the control of minimal L infinity norm. Why?
There is a lower M that does the same.
Huh?
Because there is a lower M for which you can do the same.
Basically, it's because here you say, okay, so here is fine. You are doing maximum. Here you are doing maximum. Well, minimum, but maximum from the negative side. So here, maximum. Here, maximum. But then, if you show me this path, I tell you no. What you are doing here, right? You can do it, right, with, in the same time interval with less amplitude, right? So all the effort you are doing here plus here plus here, you can do it in the same time interval with an M which is slightly lower, but then bang bang. That's the idea, right? The gain you get on the system by doing something which is constant, 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 and then this, say, decreasing arc, the claim is you can do it in the same time interval by something which is smaller here, smaller here, smaller here, smaller here, smaller here, if you adjust this correctly so that, you know, the effort, the gain you have here is corrected in the last arc here. So that's the principle, right? So if the control is compressed to the maximum from top and down, you always get bang bang. Because if it is not bang bang, it's because you could continue compressing. Sometimes people know the bang bang principle in a different way, which is actually the same but a different way of seeing. Maybe, have you ever seen the bang bang principle, any of you? How did you see it?
Control courses.
But the bang bang often is characterized as the minimal time control.
Yeah.
So sometimes people formulate the problem differently. So minimal time, so this is the dual reading of bang bang. Minimal time control. So oftentimes what people tell you is, listen, I have, this is more, say, more classical, yeah, and more natural maybe also way of emergence of the bang bang principle. People say, listen, U is less than M. This is the power of my controller, you know. I cannot go beyond M. These are, you know, this is the power of my engine, right? And then I know I can control from x0 into x1 because I have checked the Kalman run condition, but I would like to know what is the minimal time, right? Because I know that maybe if the, as we have drawn, right? So if this is the time horizon, and this is the cost of control, right? I know that the cost of control is something like this. For very long times, it's low. For very short times, it's very large. And here, what I know is that my engine can afford capital M, right? So, or you say, okay, I have 40 liters of gasoline, and I have to go to Madrid. I know that is more than enough. I know that is more than enough. 40 liters, I can do the 300, say, 10 kilometers, right? But the question is, what is the minimal time? Because if I accelerate too much, the oil consumption will increase, and the 40 liters will not be sufficient to get there. So what is the maximal velocity, right? And what is the minimal time I can achieve with the 40 liters? So then, if you give me M, it's over there. Yeah, this is the minimal time. Of course, this is not easy to compute, right? And if you try to be sharp, there is some risk, right? If you try to, you know, if you are conservative, you get to Madrid and you say, oh, I only spent 39 liters. What does it mean? You could have done better, just going a little bit faster and consuming 1 more liter. But if you try to be sharp and you are a bit too ambitious, you don't get to the hotel. Because you will, you know, exhaust all your, you know, gas before getting to the target. Good. So minimal time control is also bang bang, right? Why? Because now this time the drawing is the same, but you have to read it differently. Assume, you know, M is given now. The M is given, right? And you have to drive in minimal time. And then you tell me, I got that the optimal trajectory was like this, M minus M, M minus M, and then there is a continuous arc. I tell you, no, no, no. What you are doing here, right? what you are doing here, you are losing time, decelerating, and then accelerating again. What you have to do is really, you know, after some time, you just brake and then accelerate again. And then you will get the same thing in a shorter time, right? So when the bounds on the control are given, typically the minimal time control are bang bang. And here we are doing just the reverse. We are doing, given a time window, if I try to minimize the size of the control, compress it maximally, then I get bang bang controls. Right? Okay. This is very nice because there is switching from plus to minus, plus to minus, plus to minus. What is the difficulty for really implementing this control? Is that you have to know when are the switchings, right? And this needs to be computed. How do you compute? Well, I mean, a possible way of doing is you go back to the functional you have to minimize. You actually minimize this functional. In this way, you get the solution phi. And then you check what are the time locations when the sign of by star phi is switching. Every time the sign switches, the control jumps. Okay? And of course, you know in which direction you are jumping. You will jump from negative to positive or from positive to positive whenever the jump warning is given, right? And the jump warning is given whenever there is an effective transition. Of course, if for instance B star phi touches 0 and goes up again, and there is not an effective sign chain, you don't activate the switching, right? So you activate the switching only when there is a crossing. Okay? Of course, all this theoretically is very nice. In practice, it's harder to do, right? Because numerically, what you will see, you will never get this in a continuous manner so that you can really compute exactly when the switching is. What you will see is you know, some discrete approximation, right? And then you will have to, you know, determine when the switching is occurring. This is not something easy to be done numerically, right? So this is actually quite unstable and it can be subtle, right? So numerically is much easier to, right? Numerically is much easier to, for instance, when you are dealing with fluid structure interaction, right? So this is the water and this is a ship, right? It's much easier to deal with water motion here or dealing with elastic deformations here than determining in a sharp manner the interface, right? Of course, the interface is much more delicate, right? And in this computation, if you want to compute actually the minimal time, this is a hard exercise because you need to be very, very precise about the switching points. And this needs, of course, what? Of course, it requires of some grid refinement, right? And the more precision you want on the switching times, you will need a grid which is finer and finer and finer, right? Okay. Pontryagin maximum principle. Do you remember? Did you see this movie, Hidden Figures? I think it was. This black lady is working on the blackboard to compute. Sorry?
The women who worked for NASA.
Yeah, NASA. Yeah, so they were computing the trajectory for one of the Apollo, you know, shuttles to come back to Earth. So what was the problem for them? The problem for them, in principle, well, I don't know how true it was. So Pontryagin was working in the, you know, in the Soviet Union, of course, and he developed Pontryagin for, you know, for these, you know, space missions, right? So why is this related to that? Well, you remember, you go to the moon, and then you have to come back. When you come back, you are coming back in this small, say, you know, Apollo, which is smaller than any car we can imagine, right, and more uncomfortable. You are coming back, and you expect to land or actually take, you know, contact with the ocean in a place where soon after there will be a boat, you know, helping you, right? Because otherwise you will sink. So then somehow the point where the shuttle has to, you know, take contact with the ocean is determined a priori. This is one of these helidromes, right? When you see a circle with an H, right, meaning that the helicopter has to land there, right? Well, there is some error allowed, but it has to be in this circle. The same for the Apollo. So the exercise they had to solve is what were the main decisions to be making, right? To be making, in particular, when they should get into the atmosphere, so that once they penetrate into the atmosphere, they will be attracted by gravity and they will jump there. So it was computing the switching time. So all the movie is about computing one of these switching times. Except that in that movie, the switching is more delicate because it's switching from one dynamics to the other. Because out of the atmosphere, you have a dynamical system, and once you get in, you have a different dynamical system. So this is even more delicate, because here the dynamics is the same. It's always given by A. I'm just taking the decision of when do I switch from the minus strategy to the plus strategy. While in the other case, there is a nonlinear effect that whenever I decide to switch from one strategy to another, the dynamics of the car, or in that case, the shuttle, will change. So this is more like hybrid cars, right? Hybrid cars are what? Are like, I have electricity, I have gasoline, I have two engines, and I have to take the decision of, which one I should use anytime, right? So this is switching, but it's switching in a different way. And of course, the dynamics is switching as well. Okay, now that we are talking about switching, oh, sorry, I'm going in reverse. How do I do switching? Well, this is the typical configuration of the car, right? First year, second year, third year, and so on. Whenever you switch from one to another, the dynamics of the system is changing. Right? This is what makes the problems complicated. It's not that I have a dynamical system given by A, and that I am simply considering different control strategies like electricity or gasoline, right? These are the two controls I have. But rather that whenever I decide to implement one or the other, the A is switching as well. This is much more complex, right? The control of switching systems can be quite complex because of this nonlinear change from A1 into A2, right? So please keep in mind this. Even though the A1 system is linear and the A2 system is linear, a dynamical system in which you switch from one to another can be nonlinear because the switching is a jump, is a nonlinear process. Okay, so don't be naive. You will never be able to deal with switching systems by using linear theory. What I'm telling you here is that using the same ideas and linear theory, you can implement a switching control strategy for the same linear system. Right? This is like two people that have to, implement some work, right? We have to write, the two of us, we have to write a long paper, we have a deadline, and then we decide how do we implement this switching strategy, right? I work today, I transfer the file to you, and then you continue tomorrow, and so on. So this is a joint effort, right? Switching effort between two, cooperative forces to achieve a given goal on the same dynamical system. But we are not switching the dynamics in some sense, right? Although, in this case, it will be switching dynamics because he probably types faster in tech than I do. Then, in practice, it will not be exactly the same dynamics, right? But what I'm saying is that what we can do with the ideas we have implemented so far is doing this, the same dynamics with two controls. So be careful because switching systems are delicate. The stability of switching systems is delicate. This is very much related to this Turing instability, right? Turing, Turing, did you ever heard about Turing? Yeah? Yes, right? So everyone knows how Turing. And he did many things, right? In particular, he was, the guy of Enigma, right? He was somehow one of the pioneers in the modern computer sciences. But he was also working in mathematical biology. He was interested on patterns in nature. And he observed that patterns in nature were related to, this is a pattern, right? So there is basically white and red with a complicated interface and, and pattern of distribution of red and white. Okay? So he observed that this was related to instabilities on dynamical systems, right? And one of these instabilities is associated to switching, right? The reason is the following, sometimes there are stable dynamics that in a switching interaction they can lead to an unstable process. So let me draw you two stable dynamics, right? So one is this. So our trajectories which are going down to 0 doing this, okay? So this is a stable dynamical system, right? So this is like an harmonic oscillator with damping. Just I have put, different, say, weighting on the energy so that, the trajectory is flat that way, horizontally. And then I take the other one. In which the dynamic is stable, say vertically, following these ellipses that are stable vertically. And now I decide to switch, right? I decide to switch. And I jump from one to another and then from the other to, left to right. So I am combining the dynamics in different, say, ways. Both of them are going down to 0. Can you guarantee that the switching dynamics goes down to 0? Huh?
Intersected dynamic.
What is the intersected dynamic?
If you stay in the intersection of the two, then you're always like going towards 0.
Yeah, well, but I don't know whether I am. What I know is that this is, say, I have to do a work, and I can use the left hand and the right hand, and I have to switch. And I am doing it in a more or less intuitive manner. I didn't organize my plan carefully. So I do sometimes with the left, sometimes with the right. And I would like to know whether finally, I'm pushing the trajectory to equilibrium. So when I push with the left hand, the trajectory follows this flat trajectory. When I push with the right hand, the trajectory is doing this. So in both cases, I know that if I was all time pressing with the right hand, the trajectory will go down to 0 exponentially, according to the orange path. If I press with the left hand, the trajectory will go down to 0 according to the horizontal, say, spiral. And now I am doing a switching. Because I'm getting tired, so I do it, but I not do it in a very organized manner. I just do it whenever I feel I'm getting tired. Can I guarantee that it's going down to 0? Why? Why? You seem to be convinced that.
Using some pattern, you can grow to this.
Right. So assume I decide, I take the bad decision. I was following, I was pressing with the left hand, right? I was here. And I decide to switch in here. I will jump to a trajectory, that was very far away, right? And this will bring me very high. And then if I have the bad idea of switching when I was up there, this will drive me to a trajectory that is up there. This can easily converge. So this is why switching systems are very hard. Because you can, switch from stable systems and get something unstable. And this is what Turing said. Be careful. If you take two matrices that generate a stable dynamics, the superposition can generate unstable dynamics. Right? Simply because, one matrix can be stable in some, say, bases, and the other one in a different basis, and they don't cooperate, right? Okay, and what does switching have to do with adding matrices? So adding matrices and switching is related? Yes, through splitting. Very good. You got it. Okay? So splitting is the one that explains that switching systems corresponds to adding matrices, right? Because the dynamical system generated by A1 plus A2 can be understood, as we have explained, by switching. This was Lee's theorem, right? Like the interaction, say, intermittent interaction between A1 and A2.
Gilbert, the strands.
Well, the strand was a bit more sophisticated. This is the one you have to look. The classical one was by Lee. A1, A2, A1, A2. The most simple one is by Lee. Okay, so you see that there is a connection between a splitting method, switching systems, and this is why it's not that easy to guess what's going to be the stability of the system out of A1 and out of A2. You have to really think globally in a combined manner. Of course, when you are switching systems, you have to be even more carefully about, you know, what are the times in which you switch. Of course, I said there is a danger of instability, but if you are smart, you can also succeed on stability, right? Because then I will do what? I will, rather than switching here, I will switch at that point, then I will get here, then I will get there, I will switch again, and this will go down exponentially very fast. So the switching between two stable systems can be stable, but can also be unstable. And I have to take correct decisions about switching. This is why all the movie is about when is the switching point from out of atmosphere to in atmospheric travel.